All right, so this is chapter 14, which is all about solutions. And so, what a solution is it's a homogeneous mixture made up of two or more substances. And these two or more substances have names. So, the solute is the substance or substances that are being dissolved. And then the solvent is the one that is doing the dissolving. Now, typically, the solvent is the one that's present in a larger amount. When we think about most of our solutions are what we call aqueous. And aqueous just means that it's dissolved in water. So in that case, if we had salt water, salt would be the solute and our solvent would be the water. Now, solutions can exist in all three different physical states. You could have a solid solution, which would be something like a metal alloy, meaning maybe you melt down zinc and copper to make brass. You could have gas solutions such as air. Air is made up of nitrogen, oxygen, and other gases. Or you could have liquid solutions, and that's what we're going to primarily discuss in this chapter. And most of our solutions are where water is the solvent, meaning it's called aqueous. Now, here are just some different examples. We've got gas. Gas phase solution would be air. You dissolve oxygen and other types of gases within nitrogen. Nitrogen is the majority of our air. Many of our solutions are liquids. So soft drink, for example, would have gas dissolved in water, our carbon dioxide gas dissolved in water. The solid ones are a little bit weirder to think about. So we can dissolve gas within a solid. That would be called hydrogen and palladium. We use that in different experiments in different labs to measure the amount of substance within a solution. We've also got liquid being dissolved in liquid. So the rubbing alcohol you buy from the store that you use in your house, that's actually isopropyl alcohol that has some water dissolved into it. We have salt water, for example. That's a solid salt being dissolved in liquid. And then we've got a solid phased solution such as brass, which is zinc being dissolved in copper when we melt them together. Now, it's important to remember that solutions themselves are mixtures. They are not chemically bonded to each other. They're just mixed together. And so when you think about all those different examples, we're just mixing them together. We're not bonding them together. So we have a process called dissolution. Another way to think of this is dissolving. So when we have something like sugar, when we dissolve that into water, what we get is the sugar molecules being distributed amongst the water molecules. But if we take ionic solutions, such as something like potassium dichromate there, K2Cr2O7, I know we don't talk about dichromate too much, but Cr2O7, that is an ion itself with a -2 charge. So when we dissolve that into water, what we're going to get is we're going to get two potassium ions and one dichromate ion. And so when we have ionic solutions being dissolved, that's when they're going to split into their specific ions. So if we have two potassium ions and one dichromate ion, you're going to have three ions dissolved in solution in total. Now, if we take a look here at dissociation, or dissolving is another way to look at it, what happens is that your water molecules are going to surround the ions and pull them away. Or, for example, if it was sugar, it would surround the different parts of sugar and pull them away. If we remember back to polarity, remember that the hydrogens are partial positives. And so that's why the partial positive hydrogens are closest to our chlorine. And then if we take a look at our potassium up here, the potassium has our partial negative oxygens closest to the positive potassium ions. So you can see here we've got the negatives of the oxygen parts of the water attracting to the positive ion, and then the partial positive of the water molecule, which is the hydrogen, attracting to the negative ions. Now, if we form solutions, what's really happening is that we need to break some attraction between the water molecules. We need to form an attraction between the water molecules and whatever we're trying to dissolve. And then we've got to pull those particles apart to actually make solution. Now, there's really energy involved in this. We don't get into it too much, but there's energy when we force the attraction, and then it takes energy to actually break them apart from one another. So if we think about this as potassium and chloride, like the last slide, it is going to release energy when the water attracts to the ions, but when we split those ions apart from each other, that's going to take some energy. Now, here are the traits of solutions. They're homogeneous, meaning that you have your particles mixed evenly throughout. The dissolved solute is the size of a molecule or an ion. So essentially what that means is that whatever you're dissolving into the solution must be incredibly tiny. It needs to be on the size of a group of atoms or an atom all on its own as an ion. So incredibly tiny. The solution is colorless or transparent, so a lot of times it will be completely clear and you can see through it, but sometimes it does have a color to it, kind of like Kool-Aid. It has a color to it, but you can still see through it. It's transparent. The dissolved solute will not settle out or separate from the solution even if it's heavier than the solvent, meaning if we take something like iron 3 chloride has a higher molar mass than water. Even though it has a higher molar mass, that does not mean that those ions are eventually going to settle out to the bottom. Once you dissolve them in solution, they will stay in solution. And then the solute can generally be separated by physical means. Usually, if we want to try to get something out of a water solution, we're going to have to boil all that water off until we're left with whatever's dissolved inside of it. We can separate out a solid with filtering, but then if we wanted to get the aqueous ions out of the water, we'd have to boil off that water. So with solutions, we oftentimes want to think about solubility. So even the most highly water-soluble compounds, meaning even compounds that really, really like to dissolve in water, there's going to be a limit to how much can actually be dissolved. And so solubility is defined as the maximum concentration of a solute that can be achieved under specific conditions. And so some terms that we need to think about would be soluble versus insoluble. So soluble means that a solid solute can be dissolved in the solvent. Things like sodium chloride can be dissolved in the water. And so on your reference document, that's where you're going to see the AQ. The AQ stands for being a compound that can dissolve in the water. Sugar is soluble as well. That's not on your reference doc because it's not ionic, but things like sugar, ethanol, that sort of thing, they are soluble. Insoluble means that the solid solute cannot dissolve in the solvent. It remains a solid. So something like calcium carbonate, which is very similar to chalk. And then these next two terms are used for liquids. So miscible and immiscible. Miscible means that the liquid dissolves in the solvent liquid. So ethanol will dissolve in water. Isopropyl alcohol dissolves in water. Hydrogen peroxide dissolves in water, that sort of thing. Immiscible means that the liquid solute does not dissolve in the solvent liquid. So oil and water do not mix. That means that they are immiscible. So soluble, miscible means that they will dissolve. Insoluble, immiscible means that they won't dissolve. So here's just an example. Water and antifreeze are miscible. So you mix the water and the antifreeze. Oftentimes they'll come already pre-mixed for you in the container that you buy from the store. And so those would be called miscible. Immiscible would be something like water and oil. No matter how much you try, those two will not mix. So the general term that we like to think of with solubility is like dissolves like. So nonpolar solvents will dissolve nonpolar solutes. So typically things that are organic, which contain hydrocarbons and hydrogen, those will dissolve other things that contain just carbon and hydrogen. And then polar solvents will dissolve polar solutes or ionic solutes. So when we think about polar water, it will dissolve other polar molecules or it will dissolve many ionic solutes. So when we think about why or how much of something can be dissolved or how soluble it is, we really need to think about what the interactions between the solvent and the solute are. So solvent meaning water, solute meaning the thing we're trying to dissolve. So what are the interactions between them? What's the temperature that it's happening at? And when we're thinking about dissolving gas in a solution, what's the pressure as well? So when we think about the temperature and solubility of gases, the solubility of gases decreases as temperature increases. Okay, so you can dissolve less gas inside of a warm solution than you can in a cold solution. And some different examples of this would be maybe on a warm summer day, you take a nice cold glass of water out of your fridge. You don't see any bubbles in it at first, but then as the glass of water slowly warms up, you start to see bubbles forming on the glass. That is because some of that air needs to come out of solution as the water warms up. You'll also see on the right-hand side of this slide, this is a fish die-off. We sometimes see this in our lakes here in Wisconsin, but a lot of times we'll see it in the ocean as well. And so what happens here is that if the water gets too warm, there's not enough oxygen in the water for the fish, and so those fish eventually die off. When we think about pressure and gas solubility, what we really think about here is that as the pressure of the solution increases, the solubility also increases. And so there's this Henry's law. You don't need to know that. What I really need you to know is that as the pressure of the solution increases, the solubility increases. And so when we think about this, I want you to think about a bottle of soda. So when you have that bottle of soda before you've opened it, it's under extremely high pressure and you don't have any of those carbon dioxide bubbles coming out. But as soon as you take the cap off, what happens there is that the pressure inside of that soda bottle is going to decrease to whatever the atmospheric pressure is. And as it decreases, that's when you start to get that fizzing. So you get a lot of fizzing from warm soft drinks. And the reason for that is because when you have a warm solution, you have less solubility for gas, but also when you decrease that pressure, that's when those gases come out. So warm soda leads to a lot of fizzing. So to review there, increased temperature is decreased solubility for gases, but increased pressure is increased solubility. I want you to think about soda for pressure, and I want you to think about a glass of water from a cold fridge to a warmer setting for temperature. When we think about temperature and solubility of solids, increasing the temperature is almost always going to increase our solubility. So for the most part, as we increase the temperature of the solution, we will be able to dissolve more ionic or solids into that solution typically. So this is what we call a solubility curve. And we can see for the most part, those gases, which would be HCl, it would be the NH3 and the SO2. You can see those three lines decrease. The rest of them are slightly increasing or dramatically increasing. Those are your solids. Now, when we deal with a solution, we can think of it in three ways. We can think of it as being saturated, unsaturated, or supersaturated. So when a solute's concentration equals its solubility, that's known as saturated. When its concentration is less than its solubility, it's known as unsaturated. And when it's greater than what its solubility is supposed to be, it's called supersaturated. So when we think about a saturated solution, what happens to a saturated solution is that if we were to try to add solute to an unsaturated solution, you would still be able to dissolve more. If you added solute, again, solute, think about like salt. If we added salt to a saturated solution, it won't dissolve and it'll just go to the bottom. And then supersaturated means that you will have more solute in solution than should happen. And supersaturated is a really special case. It doesn't happen super often. There's only a few that make this happen, but what happens with a supersaturated solution is that you have more solute in there than is supposed to be. And so as soon as you make that solution unstable, either by adding another crystal of salt or by, really jostling that solution around, it will usually come out as a crystal. All right, so what they did here with this compound here, this is a supersaturated compound, is they dissolved more solute into that water than is what is supposed to be dissolved. And then what you're seeing here is they most likely dropped one more crystal into that flask after it's all been dissolved. And when that crystal comes in, what that's going to do is it's going to force all the rest of that whatever's dissolved in there to come out of solution. So this is what supersaturated solution looks like. And again, to be supersaturated, it is not very common. It's pretty tough to allow that to happen. So when we Right, so this is the solubility curve, and we can use the solubility curve to determine a few things. So the first thing would be to figure out what kind of solution is made. So unsaturated would mean that it's under the line, saturated would mean that it's exactly on the line, and supersaturated would mean it's above the line. So let's say that we had 50 grams of sodium nitrate at a temperature of 70 degrees. What we're going to do is we're going to plot that point. So we're going to go 50 grams, 70 degrees, and then we're going to take a look at it in relation to the line that we care about. So this one is sodium nitrate. So we care about this line here. And since that point is below the line, we would call that unsaturated. Now, let's say there was a point that landed directly on the line. Let's say that it landed right here. Okay, so let's say that we dissolved 85 grams of KNO3, potassium nitrate, at 50 degrees Celsius. That would be what we call a saturated solution. Okay. The other thing we can do with solubility curves is we can figure out when we become saturated. So we would be given a certain temperature. So let's figure out how many grams of Ki can be dissolved at 10 degrees Celsius. So what we would do is we would go to 10 degrees Celsius. We'd hit the line that we care about, so Ki, and then we would take that over to the grams line and figure out what that is. So about 135 grams can be dissolved in 100 grams of water at 10 degrees Celsius. So we've got a few problems here. The first three are asking you what kind of solution we make, and the second two are asking you how many grams of the different things can be dissolved there. So the first one, if I have 110 grams of sodium nitrate at 80 degrees Celsius, I'm going to plot that right here. And then if I take a look at my line, it is under my line. So this would be unsaturated. If I have 85 grams of potassium nitrate at 50 degrees, so 85 and 50, that is pretty much right on the line. So since it's on, that would be saturated. And then the last one, 50 grams of KCl at 40 degrees Celsius. That is right here, and it is above its line. Since it's above its line, this would be what we call supersaturated. Now the next one's how many grams of these can be dissolved in 100 grams of water. This is just asking you to go up from that temperature, find the line, and figure out how many grams. So at 60 degrees, our ammonium chloride, we can dissolve about 55 grams of that. And then our potassium iodide, if we run up to 10 degrees, that's somewhere around 135 grams. All right, so when we think about the rate of dissolving, what we're really thinking about is how many collisions happen between the solvent and the solute. The more collisions you have, the easier it is or the faster you can dissolve things. So if we want to increase the rate of dissolving, we can change the particle size. Let's say that we have a big chunk of sugar versus little tiny granules of sugar. The tiny granules of sugar would dissolve faster. That's because the smaller particles are going to result in more collisions, which gives us a faster dissolving or dissolution process. If we increase the temperature, increasing the temperature is typically going to increase the rate of dissolving because our water molecules are now moving around faster because they've got more energy. If they're moving around faster, they've got more collisions, which means that it's going to dissolve faster. Concentration. This one's kind of interesting. As we increase the concentration, meaning as we dissolve more and more substance within, for example, water, it is going to become harder to dissolve that. So as you increase the concentration, it's going to become harder and slower to dissolve things because there's less collisions because those water molecules are already paired up with something. They've already grabbed onto an ion or a sugar molecule, and they aren't allowed to really grab onto anything more. So concentration, as concentration increases, our dissolving process decreases a little bit. And then agitation or stirring. By moving those particles around, we're allowing for more collisions, which means a faster dissolving or dissolution process. Now, the big part of this chapter would be concentration of solutions. So we're going to cover these different concentrations. We've got mass percent, volume percent, mass per volume percent, and then molarity. Molarity is going to be the big one that we use the most often, but we are also going to learn about the other three. So mass and volume percent is found by taking the amount of solute, okay, so the smaller amount divided by the total amount in solution multiplied by 100. So what is the mass percent of dissolving 2.5 grams of sodium chloride in 50 grams of water? Well, we're going to take the mass of the solute, 2.5 grams, divided by the total mass. Now, the total mass here is not 50 grams, it's 50 plus 25. So we've got to take that 2.5 divided by 52.5 times 100, and that gives us 4.76% by mass of sodium chloride. The next one is volume. Volume works the exact same. You're going to take the volume of what we're looking at divided by the total volume times 100. So in this case, we're looking at 20 milliliters of ethanol dissolved in 80 milliliters of water. So 20 milliliters divided by 100, because 20 plus 80 is 100, times 100 gives us 20%. Now, mass per volume percent is a little bit different. In this one, we have to take the mass in grams and divide it by the volume in milliliters and times it by 100. So you have to make sure that your mass is in grams and that your volume is in milliliters. If they aren't in those units, you got to do a little bit of unit conversion to get them there. But this one, there's no adding anything because we've got mass and volume are two different things. So you can take them for what they're worth in this problem. So what is the mass per volume percent of 3.75 grams of potassium nitrate dissolved in 125 milliliters of water? Well, we're going to take the 3.75 divided by 125, multiply it by 100, and we get 3%. So for this one, figure out the following concentrations of the problems. The first one, you're figuring out mass per volume percent. The next one, you're figuring out mass percent. And the third one, you're figuring out volume percent. Remember, some of them you're going to have to add the two amounts to find a total, and one of them you will not. All right, so this first one, mass per volume percent, is grams over milliliters. So you're going to take your 5 grams divided by your 225 milliliters, timesing it by 100 to get 2.22. The next one, you're going to take your mass of your solute divided by the total mass. So 6.46 divided by 63.01 times 100 gives us 10.3. And then the last one, taking the volume of the smaller amount divided by the total volume. So 15 divided by 90 times 100 gives us 16.7. Molarity is the most common concentration that we're going to use for solutions. And molarity is defined as the moles of solute per liter of solution. Now, molarity is abbreviated as M. It's a big M, not a small m, and you can't abbreviate molarity any other way. So you either have to say molarity or you have to write it out using a big M. And so molarity can be used as a conversion because, remember, molarity really tells me moles per liter. And so we're going to be able to use that as a conversion factor in our problems. So to calculate molarity, you need to have the moles of solute and the liters of solution. Okay, and so if you're trying to find molarity, you're going to have to get your amount to moles, and you're going to have to get your volume to liters. So usually our amount is in grams, and our volume is in milliliters typically. So you have to get those to moles and then to volume, divide them, and you can find the molarity. If we were given a molarity, we can use it as a conversion factor. So if something says 2.5 big M or 2.5 molar or 2.5 molarity, something like that, you can use that in one of two ways. We can either use it as 2.5 moles per 1 liter, or we can use it as 1 liter over 2.5 moles. Now, you should never, ever use molarity to start a problem. Your molarity is always used as a conversion factor. Never start with molarity. So once again, this is our mole map. Molarity is going to be used here when we think about going from liters of solution. Technically, we can start with milliliters of solution. We just have to do a little math to get there. But we're going to be involving these solutions here. So you can start with milliliters or liters of solution, but you can only get to moles from there, and you can only get to moles using that molarity. Now we can get over to grams if we want. We can use that molar mass. And then we'll talk about stoich here in a little bit. So what is the molarity of dissolving 25.00 grams of sodium hydroxide in 1.50 liters of solution? Well, in this case, we are going to want to get the grams of sodium hydroxide into moles, because remember, the definition of molarity is moles per liter. So we need to get our amount into moles. So find the molar mass, then get us out of grams into the moles. So in this case, 25 grams is really 0.625 moles of sodium hydroxide. And then you're going to take it and divide it by the liters of solution. In this case, I was nice to you and gave it to you in liters, but if it wasn't in liters, you're going to have to most likely get it from milliliters into liters, remembering that there's 1,000 milliliters in a liter. The next type of problem would be asking how many milliliters are in solution given a mole amount. Technically, we could be given a gram amount here and a molarity. So if we start here with moles, we're going to want to get into liters and then finally into milliliters. So we're starting here with moles. We are using our molarity. You can see here our molarity is used a little bit differently. So your 0.750 is not always on top. This number is always going to go with moles, and then liter always gets a 1 in front of it. So you always have to remember that. The number associated with the big M goes with moles, and then the liter always gets a 1. So in this case, we're starting with 0.5 moles, cancel out, into liters, and then out of liters and into milliliters, using that 1,000 to 1 conversion there. Now, technically, we could have started here with grams. If we started here with grams, we would have wanted to go from grams of sodium chloride into moles of sodium chloride. And so instead of starting here with moles, you would have started with maybe 50 grams of sodium chloride. Then you would do your molar mass conversion. So grams of sodium chloride per 1 mole of sodium chloride. And I believe that is 58.44. So that's how you would start with grams. You would not start here with moles. You would have started with grams, used the molar mass conversion, and then we can move on and use the molarity here to get us out of moles and into liters. And the last one, how many grams of calcium chloride need to be dissolved in 1.5 liters to make 0.600 molar? So in this one, again, do not start with your molarity. We're going to start with liters. We're going to get out of liters into moles using the molarity itself, remembering that 0.600 goes with moles and liter gets a 1 by it. And then we're going to get out of moles and into grams using the molar mass. So finding the molar mass there, if we take a look at our units, our liters cancel, our moles cancel, and we're left with grams. This is our molarity conversion there. When it says 0.600 big M, remember that 0.600 goes with moles and 1 goes with liters. So I want you to perform these 3 calculations here, and then we'll go through the answers. All right, so the first one is asking you to, First one was asking us to figure out what is the molarity by dissolving 50 grams of iron chloride into 25 milliliters of water. We're dealing with iron chloride. You can see the molar mass math up on the top right up there. And so the molar mass of iron 3 chloride is 162.20 grams per mole. In this case, we got to get out of grams into moles, and then we're going to divide it by the liters of solution. So 50 grams of iron 3 chloride divided by 162.20, that's the molar mass again. That gives us 0.3083 moles. Our 225 milliliters in liters is 0.225. So we're going to take the 0.3083 moles divided by 0.225 liters, and that comes out to a 1.37 molar solution. The next one, to find grams of iron chloride required to make 50 milliliters of 0.5 molar solution. We're going to start here with milliliters. We're going to get it into liters, then we're going to get it into moles, and then into grams. So we're starting here with our milliliters from the problem. Then we get it out of milliliters into liters using our conversion that we always know, 1,000 to 1. And then out of liters of solution into moles using the molarity, 0.500. Big M stands for 0.500 moles per 1 liter. And then get it out of moles and into grams using that conversion factor there, using the molar mass. And then the last one, figuring out how many milliliters of solution there are if 90 grams of iron chloride are in 100 or 1.25 molar solution. So again, never start with molarity. That is always only going to be used as a conversion. We want to start here with grams. So start with grams, get it out of grams into moles using the molar mass, and then out of moles into liters using our molarity. Now, this one is where it's kind of odd to see, but remember that just because it's molarity doesn't mean that that 1.25 has to be on top of this conversion factor. The 1.25 goes with moles, and liter gets a 1. And on this case, we want moles to be canceled and liters to be left on top so that we can get out of liters and into milliliters. So 1.25 moles needs to go on bottom, and liter needs to go on top. So in this case, 444 milliliters. All right, so the next thing we're going to talk about are dilutions. Now, a dilution is when you take a concentrated solution and make it less concentrated, typically by adding water to it. So if you were making Kool-Aid that was too sweet, meaning that it's the concentrated type, then you would add water to make it less sweet, which is diluted. So you can see on the right that the concentrated solutions look darker, the diluted solutions look lighter, and then you can see there in the image, a more concentrated solution has more solute, more of what's dissolved inside of it compared to the dilute solution. So when we are taking a solution and making it less concentrated, we're going to use the following equation. M1V1 equals M2V2. Now, M1 is the more concentrated molarity. That's your initial molarity. V1 is the volume of that concentrated molarity. M2 is the less concentrated molarity, which is your final molarity, and V2 is your less concentrated volume. Now, you cannot use this equation when dealing with different solutions or different substances. The only time you can use M1V1 equals M2V2 is if you're dealing with the same substance and you're just making it less concentrated. So here's some examples. How many milliliters of 12 molar hydrochloric acid are necessary to make 500 milliliters of 1.5 molar hydrochloric acid? So you're going to make your list. We are searching for V1 in this case. And so if we take a look here, V1 is equal to M2V2 over M1. And then we plug in our units. And then we figure out our answer. It takes 62.5 milliliters of 12 molar hydrochloric acid. The next one, what is the concentration of a solution made by diluting 25 milliliters of 18 molar hydrochloric acid to a final volume of 2 liters. Now here you need to make sure that the volume units match so that you can cancel them. We can't have milliliters and liters. You either have to go to liters or you have to go to milliliters. In this case, I took them both to milliliters. So I have 18 molar and 25 milliliters. I'm searching for molarity 2, and my volume 2 is 2,000 milliliters. So if I take a look, my new concentration here is 0.225 molar. Now these ones, how many milliliters did I make of 0.750 molar sodium chloride if I use 50 milliliters of the 3 molar hydrochloric or sodium chloride? And then what is the initial molarity of a solution if 25 milliliters was used to make 0.75 liters of 0.125 molar sodium hydroxide? So if we take a look here, there's my list. The first one I'm searching for V2, and so I need 2,000 milliliters of that initial concentration. I am making 2,000 milliliters. And then the second one, my initial concentration of the sodium hydroxide was 3.75 molar. Now we're getting into stoic and dealing with the molarity with stoich. So with stoich, we can go from a different part here. Now we've got the tools that we need to go through any different part. And from here, we can, go from grams to moles to liters of solution, or we can start with liters of solution, that sort of thing. There's the molarity unit is, remember, using us as moles of a substance per liter of solution. And so we can go from liters, or technically we can go from milliliters of solution to moles of a substance and vice versa. All the other conversions remain the same. So we can go from grams to moles using molar mass, moles to liters of a gas at STP using that 22.4 liters per 1 mole, or moles to liters of a gas not at STP using our Pivnard equation. So there's 3 different types of problems that you'll most likely see using molarity in stoich up to this point. The first would be given the volume and molarity of a solution and trying to find something else. So start with a volume in liters and convert it to moles using the molarity. And once you have it in moles of that substance, you can go to the moles of a new substance and whatever else you need for that substance, whether that be grams or liters of a gas, or you can technically go all the way to milliliters of a solution using molarity as well. Let's say you're given info about one substance and trying to find volume of a solution giving the molarity of that substance. So we are told maybe like grams of a substance, and now we're trying to find the volume of a solution. What we would do is we would get to moles of a substance using that info. So let's say we were given grams, we're going to try to get to moles of that substance. Then we'll get to moles of the substance that's in solution. And finally, we will use the moles of that substance and divide it, or use that molarity to get us into volume. And then lastly, if we're given info about one substance, let's say again, maybe we're given grams of a substance and we're trying to find the molarity, and we know how much volume of a solution we made. So we're going to get to moles of the substance you want the molarity for, and then you're going to divide it by the stated volume in liters. So this is the first type of problem. We're given the volume and molarity of a solution, and we're trying to go somewhere else with it. So how many grams of calcium carbonate can be formed by reacting 15 milliliters of 2 molar calcium chloride with sodium carbonate? So here we're going to start with milliliters and go into liters. Then we're going to go into moles of calcium chloride, and then moles of calcium carbonate. And then lastly, will get us into grams of calcium carbonate. So I start with my 15 milliliters. I get it out of milliliters into liters, out of liters into moles, and then we do the mole-to-mole ratio. Then we do the molar mass. So we end up with making 3 grams of calcium carbonate. Now let's say that we were given info about one substance and we're trying to find the volume of a solution given the molarity. So if we made 13.5 liters of hydrogen gas at STP, how many milliliters of 6 molar hydrochloric acid were used? So here we're starting with liters of hydrogen gas. We're going to moles of hydrogen gas, into moles of hydrochloric acid, then into liters of hydrochloric acid using our molarity, and then finally into milliliters using that conversion. So 13.5 liters, and then out of liters of gas into moles using that 22.4. Then our mole-to-mole ratio, 1 to 2. And then here's our molarity. Please notice that the 6 molar turns into the 6 goes with moles, and then the 1 goes with liters. So at this point, the moles is on the bottom, and then out of liters and into milliliters. And then the last type, let's say we're given info about one substance and we're trying to find the molarity of that other substance, and we need to know the volume of that substance. So what is the molarity of sodium hydroxide if 25 milliliters is reacted with 8.75 milliliters of 0.5 molar sulfuric acid? So here we're going to start with milliliters of our sulfuric acid because we know the volume and we know the molarity of that. You need to know both of those in order to get started with that. So we're going to start with milliliters of sulfuric acid using the molarity. We're going to get into moles. Then we can use the mole-to-mole ratio. We need to stop there. So once we have the moles of sodium hydroxide, divide it by the liters of sodium hydroxide to get our answer. So we're starting with that 8.75 milliliters of sulfuric acid, get it into liters. Then we can get out of liters into moles using our molarity, and then the mole-to-mole ratio to get us into moles of sulfuric acid or sodium hydroxide. So then we take our milliliters and turn it into liters, and then take that the moles of sodium hydroxide divided by the volume in liters, and we get 0.350 molar. So you are going to use this equation for both of these, balance it, and then number one asks how many grams of iron would be needed to react with 25 milliliters of 9.00 molar sulfuric acid. So for that one, you're going to start with volume of sulfuric acid, use the molarity to get to moles, then to moles of iron, then to grams of iron. The next one, how many liters of hydrogen can be produced at 25 degrees Celsius in 0.850 atmospheres if 7.85 milliliters of 3 molar sulfuric acid is used? So here you're going to start with volume of sulfuric acid, use molarity to get into moles of sulfuric acid, out of moles of sulfuric acid into moles of hydrogen gas. You will stop there and then use that as N in your Pivnert equation with the temperature and pressure provided. So here is the answer to number one. We're going to go milliliters of sulfuric to liters of sulfuric to moles of sulfuric to moles of iron to grams of iron. So we're going to start there with the 25.00 milliliters of sulfuric acid, get us out of milliliters and into liters, and then out of liters into moles using that molarity. So 9.00 m is 9 moles per 1 liter. Then we use the mole ratio, 3 moles of sulfuric to 2 moles of iron, and then the molar mass of iron at the end. So we get 8.38 grams of iron. Number two, how many liters of hydrogen can be produced at 25 degrees Celsius in 0.850 atmospheres? So for this one here, you're going to run a stoichiometric problem that goes milliliters of sulfuric to liters of sulfuric to moles of sulfuric to moles of hydrogen. You're going to stop there, use that moles of hydrogen gas as N to solve for V in Pivnert. So we get 0.02355 moles of hydrogen. And then for this one, you're going to use that as N. We give our R value. Our temperature is 25 degrees Celsius or 298 Kelvin. And then our pressure is 0.850 atmospheres. So we can produce 0.678 liters of hydrogen gas. Now, if we want to do limiting and excess reactant problems, we're going to use the exact same skills that I just taught you to figure out the amount and the unit of the substance that the question is asking for. So remember, look at the question, look at the unit that it's looking for, and solve both those problems to that exact same thing. And then take the actual amount of product that you can make and go back to the unit of the excess reactant to find out how much is used. And then you'll have to do that little subtraction problem. So this one's asking how many grams of calcium carbonate can be formed by reacting 15 milliliters of 2 molar calcium chloride with 20 milliliters of 1.8 molar sodium carbonate. So for this one, we're going to start with milliliters of both the solutions, use the molarities to get out of the volume and into moles of those. Then we use the mole-to-mole bridge to get into moles of calcium carbonate, and then the molar mass to get into grams of calcium carbonate. So for this first one, we're starting with 15 milliliters of calcium chloride. Then we're out of milliliters and into liters, out of liters and into moles using that molarity, 2.00. Then we use the mole-to-mole ratio. It's just a 1-to-1 for this case, and then the molar mass. So that one produces 3 grams. And then the next one, 20 milliliters, out of milliliters into liters, out of liters into moles using 1.80 moles from the molarity, and then 1-to-1 mole ratio, and then the molar mass. So that one could produce 3.6, but that's not our answer. We only circle 3. Now, how much excess reactant is left over, and what is the percent yield if 2.75 grams is produced? So for this one here, we are going to go from grams of calcium carbonate that was actually produced to moles of calcium carbonate to moles of sodium carbonate to liters of sodium carbonate using our molarity there to milliliters of sodium carb, and then we will do the subtraction problem. So here we're going backwards from grams of calcium carbonate into milliliters of sodium carbonate. So Using the molar mass, get us out of grams of calcium carbonate into moles, out of moles of calcium carbonate into moles of sodium carbonate using the mole-to-mole ratio. Use the molarity to get us out of moles and into liters, and then out of liters into milliliters. So we use 16.65 milliliters. We were given 20 milliliters, so 20 minus 16.65 means that there's 3.35 milliliters left. And then the last one, we actually made 2.75 grams, but we could have made 3 grams, so our yield was 91.7%. Now, the last thing we have to talk about are colligative properties. So colligative properties are properties that change when a solvent, such as water, turns into a solution, so water with something dissolved. There's 3 things that we're going to talk about here: vapor pressure lowering, boiling point elevation or boiling point being raised, and freezing point being lowered. So vapor pressure lowering, what happens here is that the vapor pressure of a solution is lower than the vapor pressure of the solvent, meaning if we have just pure water, its vapor pressure is going to be higher than if we have pure water with some ethanol dissolved into it. What happens here is that the ethanol is going to take over kind of the surface of that of the liquid, and so it's not going to allow that water to jump out into solution as much. Boiling point elevation just means that the boiling point of solutions is higher than the boiling point of a solvent. So salt water will boil at a temperature higher than 100 degrees Celsius. Pure water boils at 100 degrees. If we've got salt water, it's going to boil above 100 degrees Celsius. And then freezing point depression, the freezing point of solutions is lower than the freezing point of the solvent. So salt water will freeze at a temperature lower than 0 degrees Celsius. And this is why we salt our roads. So the salt reacts with the water, makes a solution. And so now that salt water won't freeze at 0 degrees Celsius. It'll freeze lower. The last thing we have to talk about is osmosis, and osmosis is the spontaneous diffusion of water across a semi-permeable membrane. So let's break this down. Diffusion means moving from an area of high concentration to low concentration, and then semi-permeable membrane means that that membrane only allows water to travel through it and not solute particles. So not sugar, not salt, only water. And so the way that it's going to travel is from areas of low concentration to high concentration so that those concentrations can be evened out. If we take a look at this picture here, on the left, we've got a bunch of sugar molecules. And so over here, we've got our high concentration. So here's our high concentration. Here's our low concentration. And you can see that most of the water is going from low concentration to high concentration. And so what happens here is that we're trying to decrease the concentration here by adding water. And then over on this side, we have less water. And so when we have less water, we're actually going to raise that concentration a little bit. So we're just trying to bring those concentrations as even as we can. Now, where do we see osmosis in the body? Well, there's 3 different terms. So we've got isotonic, hypotonic, and hypertonic. And isotonic means that the concentration of a solute inside and outside are equal. And so the amount of water traveling in and out of that cell are going to be the same. So if we think about contact lens solution, that is an isotonic solution so that our eyes aren't disrupted when we put our contacts on. Hypotonic solution means that the outside of the cell has a lower concentration, meaning that the water is going to want to flood into the cell, possibly exploding it. And so here, if you were to bathe in pure water with nothing else in it, you would become bloated. Versus, on the other hand, salt water over there on the right would be a hypertonic solution. So salt water has very high solute concentration. And so that's why you get kind of shriveled after you go in a pool, is because the water has gone from your skin into the pool because the pool has a higher concentration and the water wants to leave it.